Okay, we are back here. Now section 1.3, we're going to be talking about square roots. It's a real radical assignment, if you know what I mean. And we're just going to experiment with those different ways of simplifying those, keeping in mind that, again, when we just have the regular radical root, we're just thinking principal square root. If it's got a negative in front, we want it to be the negative version. We can also do this where we can do the plus or minus, because the square root of 25 technically could be 5 or negative 5. So a nice easy way to do that is just go plus minus when we do that. So we have that. So let's take a look at what we have here. If we wanted to estimate the square root of 27, you know, it's one of those things you could think about perfect squares, and I think that's worth writing down anyway, I think. Writing these down. The perfect squares that we have are 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169. That should be pretty good, the first 13 that we have there. All right, so you can kind of estimate those if you want to, but if this is the case, I just go right to the calculator if it's not a perfect square and say, all right. If it says estimate to the nearest tenth, I would just type in the calculator. It's about 5.2. All right, now again, if we do it where it's opposite, if it's a negative, well, just make sure, type in square root of 55, well, you get that, make sure the negative's there, it's about 7.4. So just use the calculator if it asks you to estimate to the nearest tenth. Now, a lot of the times we're not going to have you estimate, we're going to have you simplify, but leave it in radical form. Okay, so if this is a case where 12 is not a perfect square, so if that's the case and we want to simplify in radical form, find two numbers that multiply together to be 12. Well, and make sure one of them is a perfect square. So we could do 6 and 2, but 6 and 2, they're not perfect squares. So 4 times 3 is a better option, because then what we can do is we can take the square root of 4 and put that in front and say, hey, that's 2 root 3. All right, now again, some other properties of radicals is that if you have a square root of 8 times the square root of 2, you can multiply those together and get the square root of 16. Now that's easier to find the square root, that's 4. It's the same thing we have here. If you have perfect squares, you can just take the square root of those individually and say 5 over 4. If they're not perfect squares, sometimes a good idea is to actually divide those. You can just take 18 divided by 2 and say, hey, that's the square root of 9, and that becomes 3. So let's look at some different ways of simplifying radical expressions. Again, we're not trying to find an estimate this time. We're going to try to simplify and leave it in radical form. Now, the square root of 32 is not a perfect square. So what we're going to do is find two numbers that multiply together to be 32. Now, make sure one of them is a perfect square. Try to find the biggest perfect square. The best case scenario in this case is going to be 16 times 2. Well, the square root of 16 is 4, so we're going to say 4 root 2 is our answer. Now, let's just say somebody chose something different. They said, okay, what if they said, oh, no, 32, that's 4 times 8, Mr. Boone. That's what we got there. Well, yeah, that still works. Square root of 4 is 2, and so we have 2 root 8. You might say, well, that's not the same answer. Well, keep simplifying, because 8 could be broken down into 4 times 2. All right, so now when we take the square root of 4, that's 2. We're going to multiply it by 2. That does end up being 4 root 2. So even if you don't choose the best one right away, you can still get there. Just whittle it down. Always best to choose the largest perfect square, though. This one's kind of nice, the square root of 25 over 36. Well, those are both perfect squares. You always want to recognize those. We would just say, all right, that's 5 over 6. Okay, so that worked out pretty easy. Don't want to really divide those if they're perfect squares. Just take the square root of those, and that'll simplify nicely. All right, a couple more here. Square root of 3 times the square root of 12. Neither one's a perfect square. So what I'm going to do is multiply those together, and we're going to get the square root of 36. Well, that worked out nice because that is a perfect square. We would just say our answer is 6. Okay. All right, now the next one, square root of 500 divided by the square root of 5. Well, those are not perfect squares. So what you can do is divide those and say that's the square root of 100. Or, as the homies would say, that's the square root of a hundo. Right. Make sure to speak homie. You don't want to diss the homies. They will bust a cap. All right, so when you do take the square root of 100, you do get 10. 10 is what you get there. So it simplifies nicely in radical form. Okay, well, as we get going here. Now, another thing we're going to do is do something called rationalize the denominator. And when you have something simplified like this, first thing I look at is see if we can divide those. It doesn't go in equally, so you can't. It's kind of a no-no to leave the square root, the radical, in the denominator. So here's a trick of the trade. What you're going to do is you're going to multiply. If that's the square root of 2, you're going to multiply by the square root of 2 over the square root of 2. You might say, okay, well, what does that do? Well, let's think about this. Well, the square root of 2 over the square root of 2 is 1. That's not going to change anything. That's the multiplicative identity. So as long as I multiply top and bottom by the same thing, it's going to change what it looks like, but it's not going to change the value. So really, I'm multiplying by 1 is really what I'm doing. Now, what advantage does this have? Well, as I multiply across here, 3, root 5 times root 2 is root 10. And then root 2 times root 2, well, that's square root of 4, which is just 2. Anytime you multiply those, it's just going to be 2. So does it look a lot more simplified? No, but technically it is because we don't have a radical in the denominator. That's called rationalizing the denominator. Okay, let's try that again. Let's try another one of those. All right. All right. Well, sometimes it works out nice. You say, okay, well here, oh wait, this actually divides into that. So root 2 goes into 8 4 times. So that's actually going to be root 4, and up top, that ends up being just a 1. Well, that works out nice because the square root of 4 is 2. This is just 1/2. Well, that's nice. Good. Yeah, so always check to see if they divide into each other, because that can simplify things really nicely too. Now, this is another case where, okay, yeah, 5 doesn't divide into 7, so what we're going to do is we're going to multiply by the square root of 7 over the square root of 7. And again, what that does on the bottom is it just makes the bottom 7, gets rid of that radical. That's really what we're looking for here. And then up top, we'd have 3, well, 5 times 7 is the square root of 35. And I know it doesn't look terribly more simplified, but because we got rid of the radical in the denominator, it is. Okay. So again, that's about as tough as it gets in this lesson. All right, other things that we'll do here is we're going to talk about adding like terms, much like we've done with x's and y's before. If we have the same radical, we can add those together. 1 root 2 and 3 root 2 would be 4 root 2. Now, if the radicals are not the same, then we can't add or subtract those together. Okay, you can only add like radicals. All right, so let's take a look at a couple and see what we're talking about. It's actually fairly easy. Well, if I take 9 root 3 plus 7 root 3, yeah, okay, that's 9 plus 7, that's 16 root 3. Think of 3 as like an x, as a variable. If it's the same radical, we just keep the radical, add the coefficients, and we're all set. So that worked out really nice. Yeah, okay. All right, what if we have subtraction, something like this? Okay, well, you're looking right away and say, hey, those are not like radicals. Make sure they're simplified. Okay, so again, it would be 6 root 5 minus, now remember, 20 could be the same as 4 times 5. Now what happens here is this becomes the square root of 4 is 2 root 5. So now make sure radicals are all simplified. Now it turns out that they are like radicals. Well, 6 minus 2, that's just going to be 4. Root 5 would be the final answer there. Sneaky. Make sure those radicals are simplified for sure. Okay. Okay, let's try a couple more here. Again, maybe an easier one to start off with here. All right, how about this? 3 root 5 plus 10 root 5. Wow, that's an easy one. That's just 13 root 5. Easy enough, right? Okay. And last one. Let's try this one. Ooh, this is not. These are not like radicals, but I got a sneaky suspicion we could probably simplify that. Did you know that the square root of 80 is actually 16 times 5? And the square root of 16 is actually 4, so that's 4 root 5. And there we go, so this ends up being negative. If you want to put a 1 in front, you can. I typically don't. It's not wrong to put a 1 in front, but I don't. We get negative root 5. All right, so have fun with square roots. Should be a real radical assignment for you. Until next time, I'm Mr. Boone.